Hello, everyone, and welcome to another episode of the Data Science Decoded podcast. Today, we have a really cool episode. We're going to review Kolmogorov's paper on Kolmogorov complexity. Mike and Nir, how are you guys?
Doing
Nir,
well, doing well. Can't complain.
Uh,
perfect.
I'm I'm also okay. So let's do this interesting paper. From which year is it? 68.
68.
Pretty fresh in our scale because we are talking about papers 190 years ago. It is just 56. Yeah,
Yeah, so that's the
fresh.
newest paper we ever
Yeah, yeah, yeah.
reviewed. I just want to give some housekeeping remarks. Some people told me that they listen mostly on like Spotify and podcasts, so they cannot see the paper when they listen. So we should give more at the beginning, like a TLDR or some overview of the paper and the motivation. So I think we'll start with that first, and then we'll try to dive deeper in the paper itself. Make sense?
Yeah,
Cool.
let's go.
So today we're overviewing the paper. The name is Three Approaches to the Quantitative Definition of Information by Kolmogorov from 68, as we said. So a little bit about him, some background I read. So he's really famous mathematician. The first Russian we have in our podcast. And actually it says here like we'll see later the original journal it was published. It was like a Russian one, and he made many contributions to mathematics and probability theory at the beginning of the 20th century. And again, this paper is one of them. Here already in 68, he was quite old. And my another point I want to say is like algorithmic complexity. Okay, so at the end, we're going to touch how it affected and affects us today as practitioners and where we see it, and it's quite often. And it also dovetails nicely into our previous paper we overviewed, the Shannon one about entropy and information. Like, and it was interesting because at the references, there are only two references at the end of the paper, and it doesn't talk about Shannon.
Yeah, Daniel, I think that the real reason for having just two references, I'm not sure about that.
Mm-hmm.
I have to say, but maybe in Soviet Union you're forbidden to put references of foreign
For
science. Maybe
yeah,
I can believe it. I don't know for sure, although I was born there and lived there for 20 years, but it can be.
that's a good point. Yeah, because he uses exactly Fisher's definition, so he probably knows about everything.
Oh
I'm
Uh,
yeah,
sure he knew. He was a
yeah,
genius mathematician.
yeah.
I'm sure he knew,
yeah,
but
yeah. It,
No doubt, no doubt.
yeah, it's exactly a peak of Cold War, right?
yeah, yeah.
Yeah,
So makes sense.
yeah. He,
And
he wasn't living in a free country. He couldn't do whatever he wants, but no doubt he knew about it.
yeah,
Yeah.
so I want to remind the listeners or the ones that didn't hear, right? Shannon's paper. Actually, it was 3 episodes because it was so long and detailed. So in this paper, he gives three definitions of information. So what is information? What is entropy? Before we go over the paper. And in order to illustrate, I thought about an example that we're going to use throughout our reading to emphasize. And it's imagine your home and you lost your keys and you have 5 rooms in your house, right? And it should be in one of the rooms. Okay, makes sense. And now, what's entropy? What's information? Okay, so Shannon's idea or definition is okay. Each room, like the key is in one, there's 5 rooms, so 1/5 of a probability that it will be there. There's 5 rooms. He has the definition of entropy is like the uncertainty. You can calculate, and you get like 2 point something bits of Shannon entropy. And let's say now I'll giving you a clue. Okay, the clue is it's either in the kitchen or in the restroom. So now there's only 2 options, right? So in a sense, the uncertainty went down. So the change of uncertainty or entropy is exactly information, the difference between them, right? Because I gave you information by telling you it's either in this room or that room. Okay, so this is like how Shannon would formalize if that was the case. And we're going to use this example throughout the reading of the paper. Make sense, Mike and Nir?
Yeah.
Yeah.
One small remark. I'm going to talk about combinatorial representation.
Yeah, he's gonna define it. So
okay. Because I have something to say about it.
Oh, cool. So we're gonna get there. So to the listeners, we're gonna see 3 different definitions of information in this paper.
Daniel, is it? Do you want to analogize what you just said about the 5 rooms or whatever the number was?
Yeah, it was 5 rooms.
To the 3, to the combinatorial, probabilistic, and the other.
We'll get there. We'll get there. So that's why I want to start with that. So then when we get there, people like, oh, now I get it.
Got it. By the way, just a small comment in the you discussed Shannon entropy. So in the analogy of the rooms, if all of the 5 rooms, 1/5 is the probability.
It's combinatorial.
In Shannon's entropy, you can assign a probability of 10%.
That's true, exactly. We'll get there. You're totally right.
Yeah.
It's not equal.
This is exactly what I wanted to say. But let's get to it.
Yeah, you're right. So the paper, the original name is the original name of the journal is Проблемы передачи информации, right, in Russian. So it's problems of information transmission. So it's actually 65, it says here. So maybe the translation to English was in 68.
Maybe and it took 3 years to translate it to English, you know. You didn't have LLMs and stuff like that. I'm joking.
And also it wasn't allowed.
Anyways, and it's a quite short paper, which is nice. And the first paragraph reads, there are 2 common approaches to quantitative definition of information. It says combinatorial and probabilistic. The author briefly describes the major feature of these approaches and then introduces a new algorithmic approach that uses the theory of recursive functions. Okay, so it says up to today there are 2 definitions. We'll go over them soon, and then I'm gonna show you a third one. And the first that he describes is the combinatorial approach. Assumes, now I'm going to read, assume that a variable x is capable of taking values in a finite set x containing n elements. We say that the entropy of the variable x is capital H equals to log 2 of n, right? So if you n elements, so you just log of n. And that's entropy. And when it says when you actually get a value, right? Before that it was the possibilities of values. Now if you get an actual value, then you get information. And it also equals log 2 of n. Anything to add about that, guys?
No, pretty basic stuff, I think.
Yeah, cool. And then he says, if the variables are independent, there's between x1 and xk. The entropy of all of them is just the entropy of each one. You add them. It makes sense, right? If you think about an entropy as uncertainty, you have x and variables. Each one has some uncertainty. They're independent. So the total uncertainty, you just add them. Okay. Still, everything is quite straightforward. Then he says information is in bits, so it has to be like a number that makes sense. And here is an example. He says the number of different words consisting of k zeros and ones. So you have k elements that either 0, 1, and then you put another number 2 there. And he says the combinatorial number of different combination you can do it is 2 to the power of k times k plus 1. And why it makes sense? Because if you had just 0 or 1s, it's 2 to the power of k ways to arrange them, right? And then you can stick a number 2 right in every place. So there's k plus 1 options to do it. So the total number of combination is 2 to the power of k times k plus 1. And now that you have the number of combinations, you can calculate the information. You apply log on that. Okay, so this is why he defined this as like the combinatorial definition of information. You have a system, you count the number of possible states, you assign, as we talked a little bit, each state like a probability of equal probability to each state, sorry. And then you calculate the information.
Yeah.
And this is like, tell me if I'm wrong, but like a private case of general Shannon entropy, right? When all the states are the same, meaning equal probability.
Yes.
Cool. That's when I was reading that, I'm like, why he didn't say anything about that? But yeah, that's the case. And then what happens here? I'm gonna continue reading. Discussions of information theory do not usually go into this combinatorial approach at any length. Okay, he says that, but I consider it important to emphasize its logical independence of probabilistic assumptions. Okay, so he still says it's important to say it's different than the probabilistic assumption. And to our listeners, probabilistic assumption is that, let's say, every room in our example has different probability. Maybe it's not equal, right? Maybe I know most of the day I was in the living room, so I'll give it higher probability that the keys are there.
By the way, Daniel, small remark. Here we're talking about the combinatorial approach. So we can't talk about probabilities. We're talking about frequencies. So the probabilities we will see in the next chapter.
You're right.
Yeah, here we're talking about frequencies, and we all know that they do some laws of probability. We can approximate these probabilities by frequencies, but here we can we have to stick to these frequencies there.
Good point. Yeah, my mind goes there because that's what I know, but that's correct. It says again, I just care about possibilities that I can combine stuff. I don't care about anything else. That's why it's combinatorial. How many combinations I can build in the system.
Yeah.
And then he says that it's easy to see that for large n, meaning, let's see where n was defined. I missed that part. Oh, yeah, it says a message of length n. Okay, so if, again, you send in a message and each letter could be in different combination. So if the message is really long, it says approximately you get n times h. N is the length of the message, and age is the
Entropy per symbol.
I think it's the information or the uncertainty of each like character.
It's per symbol, I think.
Yeah, or the symbol.
Yeah.
So it makes sense. It says approximately.
Yeah, and we know the equivalencies, right? What Mike just said.
Yeah, and here what is written after in this formula, it doesn't have a number. It is just a Shannon theorem. Then they discussed it in the very deep extent before 2 months. So this is exactly Shannon coding theorem.
Mm-hmm.
Cool. Let's continue. He says he gives another inequality here, but the important point he says, however, I will not go into the details of this special problem here. It's only important for me to show that the mathematical problems associated with a purely combinatorial approach to the measured information are not limited to trivialities.
Yeah.
Okay, now he's gonna give us like his counter. It is perfectly natural to take a purely combinatorial approach to the notion of the entropy of language, if we have in mind an estimate of its flexibility. Okay, so again, he's now going to like language and books. An index of the diversity of the possibilities for developing a language with a given dictionary and given rules for the construction of sentences. Then he discussed Ratner and Svetlana. That's one of the references. They're Russian. They estimate the binary logarithm of the number n of Russian texts of length n. So again, they just took texts and calculated the entropy at the end, like how it was how he defined it. And they get like 1.9 bits with some small variance. And he says this is considerably larger than the upper estimate for the entropy of literary texts that can be obtained by various methods of guessing continuations. This discrepancy is quite natural, since literary texts must meet many requirements beyond simple grammatical correctness. So do you follow his logic, what he's trying to say here?
Yeah, he's saying basically that if we take let's take the dictionary and let's comprise out of the dictionary all sequences that make sense grammatically. And let's count the information there. The information is about 2 bits, okay? And he's saying now, well, let's take all these sequences and take out of them whatever doesn't make sense literally. We cannot actually understand this type of sentences. So we gained information about the process, and so the complexity or the relative entropies.
Yeah, there's no complexity yet.
Yeah, no. I mean the uncertainty. Okay, the uncertainty is reduced.
Reduced, exactly.
Yeah, because there is a constraint here, combinatorically speaking.
Yeah.
We have less combinatorics or less options or combinations here, and so the relative uncertainty or the uncertainty is decreased. That's what he's saying.
Mike,
but still, you know what? For me, he's comparing here the dictionary, Ozhegov dictionary. It's pretty famous dictionary in Russia, in the Soviet Union, and he compares it to the entropy of the literary text. And for me, this number 1.9 is way lower than I would expect, because what I remember from the Shannon paper, the number for the English, the similar number for the English text is about 3.8 or 3.9 or something like that. It is much higher entropy, you know. But this dictionary have some very special structure, you know.
Yes.
The words appear in the alphabetic order. But literary text, you know, you have some coherency. The text must be coherent.
Yeah.
So for me, I can't tell you that I fully understand what is written there. Maybe there is some problematic translation. I need to see it in Russian, although I'm not sure I'm gonna understand it, because for the last paper in Russian I read was 25 years ago, but still I can try.
Yeah, I think again these 2 bits are plus minus whatever the tolerance there is the average for the whole dictionary of grammatically correct sequences.
Yeah.
So there are sequences in which you will need maybe 100 bits, but on average, if you take it to infinity, it's 2. That's what he's saying. It doesn't show it, it doesn't prove it, but I understand.
It gives a reference.
Yes, and I understand what he's saying. I don't know it to be true, but I understand what he's saying.
Yeah, but you see, the strange thing is that for the English text, the same estimate is more close to 4, I think. Maybe I'm wrong, but it just looks a bit strange from this point of view. Maybe I'm wrong. I need to see it.
Yeah, let's continue. I don't think it's important to the
it's not
understanding of the paper.
Yeah.
And then he says, okay, we're gonna review now some more properties of entropy and information. He says, at this point, let us turn to the discussion of the extent to which a purely combinatorial approach permits one to estimate the information conveyed by a variable x with respect to a related variable y. Okay, so he says then the relation between the variables x and y, which respectively take values in the sets x and y capital. Okay, he's gonna continue defining that as pairs. Then he says it's natural to define the conditional entropy by the equation, and we see that, seen that also in Shannon's paper. So the entropy of, he says y given a. So now somebody gave you more information, is the log to the power of 2 of the number of new possibilities that y can take given a. So in our case, we started with 5 rooms. Then I told you a is me telling you that now it's either in 2 rooms instead of 5. So the number of possibilities went down from 5 to 2, right? So this conditional entropy will be now lower. And this is exactly comes in the next definition of the information conveyed. And he says the difference between the entropy at the beginning, 5 possibilities, minus the entropy now, there's only 2 possibilities, is the information, because that's what I gave you, in a sense. And now then he gives an example. Doesn't really matter for our purposes here.
Why? It's actually a good example, I think.
Okay, if you think it's good, Nir, go over it. Explain it to us.
Okay, so he's saying he's trying to convey the message that sometimes a conditional variable x that can attain a value a is influencing our information given to the variable y. That's what we call today mutual information. And he has a table of y going from 1 to 4, which is 2 bits, and x is going from 1 to 3, and he's putting plus and minuses inside the table, plus to denote that every value is valid. Okay, so for example, for x1, all the y's are pluses, which means that for x equals 1, the values of y can attain four
options,
values, which is 2 bits. So the mutual information is 2 bits. For x equals 3, we actually see that y has to be the number 2. Okay, so if we know that x equals 3, we know that y equals 2. And that means that the mutual information we gave by introducing x, we gave back 2 bits of information. So we know everything about y now.
Yeah, because it's in one state.
Exactly, because it's actually deterministic. So we gave all of the bits back as
Yeah,
information. Yeah,
it's like me saying the keys are in the living room, right?
exactly,
So the five possibilities become one, and
exactly,
I gave you a lot of information.
exactly. The 3 point something bits, right? Yeah.
Yeah.
Yeah, and I'd like to emphasize very small remark. We
Mm-hmm.
are not talking about probabilities here. We are talking about frequencies. This
Mhm.
this problem, all what Nir said, we need to
Mm-hmm.
use word frequency, and all these results, all these results stay correct, even if they replace frequency, sorry, probability by frequency.
Mhm. Mhm.
Yeah, and then he says it's obvious that the entropy of x given x is zero. I don't give any information. And
Mhm.
if I give you all the information, then it's just the entropy. So that's like trivial. Okay, now the second approach, uh, the probabilistic approach, chapter number 2, says the possible advantages of further developing information theory on the basis of the previous definitions have been overshadowed by the fact that if we make the variables x and y random variables with a given joint probability distributions, we can obtain a considerably richer systems of concepts and relationships. Okay, it says paralleling the quantities introduced previously, we have now the entropy as defined exactly like in Shannon's paper, right? It's sum of the probability of x times log in the basis of 2 of the probability of x.
Mhm.
And then there's also the conditional entropy,
Yeah.
y given x, and also there's the definition of the mutual information.
Yeah. And in the paper, it denotes everything that is probabilistic by sub W.
Exactly, yeah. So now it's
Yeah.
age with subscript of w,
Yeah.
which w means I don't know.
Probabilistic.
Yeah,
No,
uh, maybe in Russian.
Yeah.
I'm
Maybe.
not
I don't
sure.
know.
I'm not sure.
And then he gives the properties, um, which is cool. So again, in our case, the example of the rooms and the keys, prior we said, there's just 5 rooms, so there's 5 combinations. Now we can assign each room some probability,
Yeah.
right? And it makes our ability to describe the problem richer in this case
Yes.
Mhm.
with more possibility. Okay, so that's the intuition for the listeners.
Actually, there is. Can you scroll up for a
Yeah.
second? So equation 11, he's saying that the entropy under the probabilistic method
Yeah,
less
is
equal than the entropy under
the
the relative frequency
combinatorial.
method, combinatorial method, which is to say that we know more information,
Yeah.
we have more information if we assign probabilities and not treating everything equally likely combinatorially.
Yeah. It just means very basic fact that we all know that the entropy of uniformly distributed random variable is the maximal if they are playing
Exactly.
with probability. Yeah, and this is exactly he calls it combinatorial and probabilistic, and I'd rather prefer to call it uniformly distributed versus non-uniformly distributed. For me, it is more understandable convention.
Yeah.
But yeah, he is Kolmogorov, and I am Mike.
Yeah, he's Kolmogorov and we are we. Right.
It says something interesting here. However, it should be noted that the probabilistic approach gives rise to a paradox. In the combinatorial approach, I, the mutual information, is always content, meaning it's like always positive, I think.
Mhm.
But
Yes.
IW in the probabilistic definition may be negative.
Can you understand it? Because there is some term of continuous entropy, And for
It
continuous
says
entropy,
here 10. 10 could be negative.
yeah, but how? I don't see any way.
Yeah.
Near, do you see?
I think there are certain probability density functions that are very skewed, so the information can be negative, like negative correlations between X and Y, for example. That's the way I see it, even though I never encountered such a
Maybe it's like confusing, like I give you some information that confuses you. Like I'm trying to think about intuition. How can more information, like given something, right? It's Y given X.
It is very strange because we are talking about some optimal use of the information you have, and if the information you get is confusing, you can just discard it and not using it. And I think a mutual information, you can prove it that for the discrete random variables it is always non-negative, but that there is some term which is called continuous entropy, and for continuous entropy,
Yeah.
all these very convenient properties may not hold. I don't remember. It is much more complicated than in the.
No, it's definitely only for continuous. Definitely, it's not for discrete. Discrete is always positive.
Yes,
you're right.
I think because maybe the continuous one, they are like abstract entities. Like discrete, you can actually map to reality. But continuous variables are abstraction.
Yeah.
Yeah, I think that it's more like discrete probabilities are always between. It's a probability mass function. It is already always between 0 and 1. So the minus there will always affect it to the positive effect. But PDF, the continuous case, can be infinitely large, right? So logarithm of a very large number can be something that is taking us negatively, I guess. If we put a minus before it. So that's I think that's the.
All right, let's continue. As
yeah,
I think like we won't solve the paradox here.
No, it doesn't matter.
And now it says the important connection to what we discussed. The probabilistic approach is natural in the theory of information transmission over communication channels, carrying bulk information consisting of large number of unrelated or weakly related messages, obeying definite probabilistic laws. So that's what Shannon did, right? Shannon's motivation was exactly communication systems. He says, in this type of problem, there is a harmless and deep-rooted tendency to mix up probabilities and frequencies within a sufficiently long time sequence. In practice, for example, it can be assumed that the problem of finding the entropy of a flow of congratulatory telegrams and the channel capacity required for timely and undistorted transmission is validly represented by probabilistic treatment, even with the usual substitution of empirical frequencies for probabilities. So he says this approach is good for those kind of problems.
And Daniel, by the way, I think we have some young listeners here, and when we need to explain to them what is Telegram. I'm not sure many of them, those who was born in the 90s, I'm not sure they know what is Telegram. And Telegram is a way to was a way to send short messages because
it's not an app.
Before beepers and before stuff like that. You go to the postal office and you send it in Telegram, and I remember it cost quite a lot of money in the Soviet Union.
No, Mike. Telegram is an app, and you can send arbitrary long messages there for free. Yeah. But what he says here is very interesting, actually, because he say congratulatory messages, meaning I think that he means that it's independent between message and message. I think that's how I understand it.
Yeah, because the next part comes. He says, but what real meaning is there, for example, in asking how much information is contained in War and Peace?
Yeah.
Is it reasonable to include this novel in the set of possible novels? Again, because we talk about probabilistic, right? We need to assign some kind of prior distribution on the novel. Like, what does it mean? And he says, even postulate some probability distribution for this set. On the other hand, must we assume that the individual scenes in this book form a random sequence with stochastic relations that damp out quite rapidly over a distance of several pages? So it's like making fun of the analogy to transmission of information in like telecommunication.
By the way, I think it is quite important observation, because the question he is asking here, we can compress War of Peace as a book in order to transmit it in some optimal way, and we can compress it as an example of the broad set of all books, and the rates in both in these cases will be different. The compression rate or the amount of information will be different, because because I think the number of laws on the broad set of books which you can leverage is larger. I think you can compress more efficiently. It is my opinion.
Yeah, and then he gives an example also from like biology and hereditary information. Like, what does it mean to look at all the possible all the possible probability distributions of some species and stuff. So to him, it's probably too abstract or something like that. He doesn't like it, and I think that's his motivation to his approach.
Yes, I think that he shows here that if you try to encode with bits all of the relevant species on Earth, it will reduce to something very funny like 100 bits.
Yeah,
and that's in his eyes is a paradox, which is that doesn't make sense.
Yeah, I think you can also interpret it as difficulties of estimating frequencies, not frequencies of symbol, but frequencies of larger subsequences of words. And it is, the bigger data set you have, it is a more complicated problem. For now, they have our supercomputers and we have GPUs, but 60 years ago, it was a very, very difficult problem from the practical point of view.
Yeah. Mike, can we draw an analogy for current days language models from here?
I think let's talk about the algorithmic approach.
Okay.
Yeah, exactly.
I'll give a couple of examples for the language models.
Yeah, so that's chapter number 3 now. Exactly.
Yeah.
That was the end of the first part, where we reviewed the first 2 chapters from his paper. In the next episode, we're going to review the last chapter, where Kolmogorov introduces his complexity. See you there.